From the window of the International Space Station, the southeastern coast of Spain presents a singular anomaly. It is not a sprawling city or a geological formation. It is a solid, blindingly white geometric patch covering over 33,000 hectares, roughly 330 square kilometers. NASA imagery confirms that this structure is arguably the most distinct human-made feature visible from orbit, far easier to identify than the Great Wall of China. This is not a glacier. It is the Campo de Dalias in Almeria, known industrially as the Sea of Plastic. To a structural engineer or a logistics expert, this is arguably the most efficient food production machine on Earth. Beneath this endless canopy of polyethylene film lies a synthetic biosphere that generates over 3.5 million tons of produce annually. This single grid supplies nearly 60% of Europe's entire vegetable demand during the winter months, generating an export revenue exceeding $4 billion per year. However, the existence of this agricultural engine defies basic physical geography. By all standard metrics, Almeria is a hostile environment for commercial farming. It is the driest region in Europe, receiving an average of just 200 millimeters of rainfall per year. For context, viable open-field agriculture typically requires a minimum of 400 to 500 millimeters. The region is battered by strong coastal winds and intense solar radiation that causes rapid evaporation. In the 1950s, this was a desolate, economically stagnant landscape where traditional farming yielded almost zero return on investment. The local farmers did not attempt to irrigate this dry scrubland in the traditional sense. They realized that fighting the environment was inefficient. Instead, they decided to decouple agriculture from the native geography entirely. They engineered a massive passive solar containment system. By covering the landscape in plastic, they trapped humidity and manipulated the microclimate. They didn't just plant seeds in the ground. They constructed a multi-layered geological filter system, known as Enarenado, that essentially tricked the desert into behaving like a tropical greenhouse. To understand how they extract billions of dollars from sand and plastic, we have to look at the specific engineering beneath the surface. It starts with a layer of clay, a layer of manure, and a mechanism that violates the capillary action of water. Layer 1. The hydraulic seal, compacted clay. First, heavy machinery must level the native terrain, which in the Campo de Dalias is largely a porous, limestone-based scree. This natural ground is useless for farming. It swallows water like a sieve, draining precious moisture instantly into the deep bedrock. To counter this, engineers import and pack down a thick base layer of layuna, a heavy, impermeable clay sourced from the nearby eroded mountains. This clay acts as a massive industrial liner. In a region where water is liquid gold, this clay seal ensures that every drop of irrigation remains trapped in the root zone, turning a porous desert floor into a watertight basin. Layer 2. The biological battery, manure. Directly atop the clay, a layer of organic manure is applied. Historically, this region was too dry for crops, so the only economy was herding. Farmers utilized this by striking a symbiotic deal with local shepherds, trucking in tons of sheep and goat manure from the surrounding arid hills. This layer serves as the fuel tank. As it slowly decomposes, it provides a steady release of nutrients while generating a low level of heat through microbial activity, a critical feature that keeps the root systems warm during the sharp temperature drops of desert winter nights. Layer 3. The thermal insulator, silica sand. The final and most critical layer is a 10 to 12 centimeter blanket of washed beach sand or grit, often dredged from the nearby Mediterranean coast or inland quarries. This is the masterstroke of the Enarenado system. Physically, the sand breaks the capillary action of the soil. In normal farming, moisture wicks upward through the soil micropores to the surface, where the sun evaporates it. However, the gaps between these coarse sand grains are too large for water to climb. The sand acts as a one-way valve. It allows irrigation water to drain instantly down to the manure, but it physically prevents moisture from wicking back up. The result is that evaporation from the soil is cut to near zero. Furthermore, the sand dictates the thermal dynamics. Dark soil absorbs heat, which can cook delicate root systems in the 40-degree Spanish summer. This white silica sand has a high albedo reflectivity. It acts as a mirror, bouncing solar radiation back upward. This keeps the root zone cool and stable, while the reflected light hits the underside of the crop leaves, significantly increasing the total photosynthetic active radiation. With the foundation laid, the plastic tents are transformed into what are essentially vertical fruit factories. The farmers here do not grow crops in patches or bushes like a traditional garden. Instead, they engineer plant towers using a technique technically known as high-wire cultivation. The primary engines of this economy are tomatoes, bell peppers, and cucumbers, but the way they grow is radically different from open-field farming. Inside the greenhouse, farmers plant the seedlings directly into the sand layer, right next to the drip irrigation lines. As soon as the plant is established, it is tied to a vertical string that hangs from the steel roof structure, which sits 3 to 4 meters above the ground. Farmers here use specific breeds known as indeterminate varieties, which are genetically programmed to never stop growing. A standard tomato plant in a garden might reach waist height and stop, but in Almeria, these vines grow up to 20 centimeters every single week. To manage this rapid growth, workers perform a weekly ritual of pruning and lowering. They strip all the side shoots and leaves off the bottom of the stem, forcing the plant to direct its energy into the fruit at the top. As the vine reaches the roof, workers unhook the string and lower the plant by half a meter. The bare, leafless bottom of the stem is then carefully coiled along the floor on top of clean plastic sheets, looking much like a resting snake. By the end of a season, a single tomato plant can be over 10 meters long, with only the top 2 meters actually standing upright and bearing fruit. This technique allows farmers to maximize the density of production, growing up to 15,000 plants per hectare. While the plants are growing, the farmers face a critical problem. Inside a sealed plastic tent, there is no wind to shake the pollen loose from the flowers. Without pollination, there is no fruit. To solve this, they do not use high-tech fans or robots. They use biology. Every greenhouse is equipped with cardboard hives of the bumblebee, known scientifically as Bombus terrestris. Unlike honeybees, bumblebees are heavy and aggressive pollinators. They perform buzz pollination, which involves vibrating their flight muscles at a specific frequency to violently shake the pollen out of the tomato flower. It is a simple, low-tech solution that works with near-perfect efficiency. You can actually hear the hum of thousands of bees working in these greenhouses, a sound that signifies money is being made. While tomatoes are the long game crop, cucumbers are the sprinters. In the heat of the Almeria greenhouse, a cucumber plant grows with terrifying speed. From the moment a flower is pollinated, it takes only 10 to 12 days for a cucumber to reach harvest size. This requires intense labor because workers must patrol the cucumber rows every single day. If they miss a cucumber by just 24 hours, it can grow too large for the strict supermarket standards and becomes unsellable waste. Bell peppers are managed differently, as they are allowed to grow into dense canopies. As the peppers ripen and change from green to red or yellow, the timing becomes a financial decision. Farmers monitor market prices in Germany or England. If the price is low, they leave the peppers on the plant, effectively using the crop itself as live storage. If the price spikes, they harvest immediately. The harvest process is entirely manual and relentless. Because the climate is controlled, the plants do not stop producing. Picking crews move through the rows, pushing carts on rails that often run along the heating pipes. Once a crate is filled, the logistics of Almeria become tighter than most airports. The clock starts ticking the moment the vegetable is cut from the vine. Within 2 hours, it arrives at the local packing house where optical sorting machines scan every tomato for size and color at a rate of thousands per minute. By the 6th hour, the produce is palletized and loaded onto a refrigerated semi-truck. Less than 48 hours after leaving the vine, that truck is unloading at a distribution center in Frankfurt, London, or Paris. This system is so dialed in that Almeria exports over 3.5 million tons of produce a year. To put that in perspective, every single day during the winter, roughly 3,000 heavy trucks leave this valley full of food. It is a masterpiece of efficiency where the sand saves the water, the string maximizes the space, The bees do the work, and the trucks move the product. But this massive output brings us to the financial reality of who is actually getting rich, and what this massive operation does to the local economy. In the most recent agricultural campaign, the Almeria province shattered its own records, generating export revenues of 3.7 billion euros. This single province now accounts for over 40% of Spain's total vegetable exports and nearly 20% of the vegetable supply for the entire European Union. The dependency is absolute. Data shows that Germany alone absorbs roughly 30% of everything grown here, meaning that 1 out of every 3 tomatoes eaten in Berlin during the winter comes from this specific patch of Spanish sand. The efficiency metrics behind these billions are what truly separate Almeria from traditional farming. The most critical number here is water productivity. In standard open-field agriculture, producing 1 kilogram of tomatoes typically requires 60 liters of water due to wind evaporation and inefficient soil absorption. Inside the plastic walls of Almeria, thanks to the Enarenado sand system and precision drip irrigation, that number drops to just 4 liters per kilogram. This represents a 15-fold increase in hydraulic efficiency. Furthermore, while a traditional soil farm might yield 5 kilograms of produce per square meter, the high-tech greenhouses in Almeria are pushing yields of 70 kilograms per square meter. They are essentially extracting 14 times more food from the same footprint while consuming a fraction of the resources. Regarding the quality of the product, there is often a debate about flavor versus consistency. While rapid growth can sometimes dilute sugar content compared to slow-growing heirloom varieties, the safety profile of these vegetables is arguably the best in the world. 20 years ago, Almeria was criticized for chemical overuse, but today the numbers tell a different story. Recent audits confirm that over 26,000 hectares of these greenhouses now utilize certified biological control methods. Specifically, 99% of all pepper crops and 85% of tomato crops in the region are now managed using predatory insects rather than chemical sprays. This massive shift has resulted in produce that consistently tests far below the maximum residue limits set by the European Food Safety Authority, making it statistically some of the safest produce on the continent. However, the most surprising return on investment is not financial but atmospheric. A peer-reviewed study published in the Journal of Geophysical Research analyzed temperature trends in the region from the 1980s to the present. While the rest of southern Spain has warmed by roughly 0.5 degrees Celsius per decade due to climate change, the sensors inside the sea of plastic recorded a cooling trend of 0.3 degrees Celsius per decade. The 33,000 hectares of white polyethylene act as a massive planetary mirror, reflecting solar radiation back into space. In their quest for profit, these farmers have unintentionally engineered a passive geoengineering system that is locally reversing global warming. But this white ocean is not without its dark depths, and the environmental bill for this success is finally coming due. The primary cost of this system is hydrological. For decades, the thousands of wells in the region have pumped water out of the underlying aquifers faster than nature can replenish them. The result is saltwater intrusion, where the Mediterranean Sea is literally seeping sideways into the groundwater tables, turning fresh reserves brackish. To survive, the region is now pivoting to massive desalination plants, effectively turning electricity into water, and then water into food. This secures the supply, but it drastically increases the energy footprint of every tomato produced, challenging the long-term sustainability of the entire operation. Then there is the physical waste. The 33,000 hectares of polyethylene sheeting must be replaced every 3 to 4 years due to UV degradation. This generates over 30,000 tons of plastic waste annually. While recycling rates are improving, a significant portion of this plastic historically ended up in illegal landfills or washed into the ocean, creating a microplastic crisis that contradicts the clean image of the biological control methods inside the greenhouses. Yet, despite these flaws, the Almeria model represents a blueprint for the future of human survival. As climate change expands desertification zones across the globe, this method proves that we do not need fertile soil to feed the planet. We only need sunlight and engineering. This model is already being studied and adapted in similar coastal desert regions, from the Baja California Peninsula in Mexico to the arid coasts of North Africa and the Middle East. It demonstrates that with enough capital and technical intervention, even a wasteland can become a breadbasket. This brings us to the final question for you. When you look at these satellite images, do you see an environmental monstrosity that covers the earth in garbage? Or do you see a necessary masterpiece of engineering that keeps millions of people from starving? Let us know your verdict in the comments below. If you enjoyed this deep dive into extreme agriculture, make sure to hit the like button and subscribe for our next analysis. Thank you for watching.